In this lesson, we're going to learn how to find all the rational zeros of polynomial functions. I want to first mention one of the most important theorems in Algebra 1. We call it the fundamental theorem of Algebra 1. And what it states is that a polynomial function of degree n has n complex zeros. That means the zeros, or the x-intercepts, have to match the degree. Now, sometimes it's going to have complex zeros and you won't see the zero cut through the x-axis. But essentially what it's saying is if I have a fifth degree polynomial, it will have 5 zeros. So this would be a case where you can see them. They would all be real. We're going to focus in this video on the rational zeros, meaning any number that can be written in fraction form. Up until this point, you've been given instructions like factor this polynomial given that x plus 3 is a factor. So that means you have a starting point to do your synthetic division. But what happens if you're not given this starting point? How do you find a starting point? Because there's an infinite amount of numbers you could test to see if they go into it evenly. So how do you narrow it down? Fortunately, there is a theorem that will narrow it down. So rather than testing every possible number, real number out there, if there is a rational zero, it will be in the list of p divided by q, where p is the factors of the constant term and q is the factors of the leading coefficient. Let's illustrate this with an example. So this polynomial function here is quartic. So I know it has to have 4 zeros, whether they are all real or whether they are complex. If it has some rational ones, it will be in the list of p divided by q. So p here is -5 and q is +2. So we're going to list all of our factors of -5. Now, your list is going to be both positive and negative. So my factors of 5 are just 1 times 5. Now, the reason it's positive and negative would be 1 times -5, -1 times +5, or +1 times -5. So you will always, regardless of whether your sign is positive or negative, your list will include both positives and negatives. Now, my factors of 2 are just 1 times 2, so 1 and 2. Now, the possible rational zeros would be in the list of p divided by q. So that means I'm going to take each of these values, p's, and divide it by each of these. So this would be 1 divided by 1 is 1, and then 1 divided by 2 would be 1/2. Then we'd have 5 divided by 1 is 5, and 5 divided by 2 is 5/2. So if this function has a rational zero, now no guarantee that it does, but if it does, it will be in the list of these 8 values. Now I say 8 because remember it's positive and negative. So you could potentially do synthetic division now 8 times to find one possibility that works. Now, truth be told, you could use technology for a shortcut and see if by looking at the graph you can identify one of the values as a starting point. But I'm just going to begin by testing +1. If that doesn't work, I'll quickly crank out one for -1 and go from there. So 2, 11, 3, -11, and -5. I'm going to quickly do the synthetic. So we got lucky. I can see that 1 works for this function. So I'm just going to mention something of a shortcut and a way we can use the graphing calculator to help us find additional rational zeros. So we know that the remainder has to be 0. So if I try f of -1 quickly on the calculator, if I get 0, then I know that -1 is also a 0. So that would be another method to test. So why don't you pause the video and see which ones work. So when I toss this in my graphing calculator, plugging in -1, I do get 0. So that confirms that -1 is an actual rational zero. So I tried it again for f of 1/2. I did not get 0. I tried f of -1/2, and I got 0. So I know that it crosses at -1/2. and then I tried 5, and it crossed at 5. So here are my 4 actual rational zeros. I don't need to test anymore because by the fundamental theorem of algebra, I know it has to have a max of, it actually has 4 total zeros, and this one happens to be all rational. All right, let's take a look at this one where we list out our possible rational zeros. So we're going to start by listing our factors of p, which would be the factors of 4. So that would be 1 and 4, 2 and 2, so 1, 2, and 4, and of course that's plus or minus. My factors of q would just be plus or minus 1. So now my possible rational zeros would be all the possible combinations of p divided by q. So that's going to be plus or minus 1, 2, and 4, again, because if I divide by 1, that's not going to change that list. So these are my 6 possibilities. I'm going to start testing. So when I test -1, I get positive 2. So -1 is not a 0. When I try f of 1, I get 0. So my actual zeros, let's see, would be x equals 1. That's where it's going to cross the x-axis. If I try f of 2, I get -4. So that is not a 0. F of -2 looks like -10. So that's not 1. I try f of 4. Nope, and f of -4. Okay, so there is only one actual rational zero. So just to point out what this means, the other two must be complex or irrational. If you take a second to graph the function on your graphing calculator, a quick sketch, it looks something like this. So it actually does have 3 real zeros because we can physically see them. So that means one of them is here at 1 and the other 2 would definitely be irrational. In this problem, we're told to find all the zeros of the function. So again, I'm going to begin by listing my p's, which would be the factors of -6. So that's going to be plus or minus 1 and 6, 2 and 3. Factors of q, well, q is 1, so that's just going to be plus or minus 1. So my possible rational zeros would be in the list of 1, 2, 3, and 6, and then their opposites, so plus or minus. And I'm going to use my graphing calculator to quickly do g of these values. So pause the video and find one that works. And it took me a little longer this time, but I found that -3 gives me a remainder of 0. So I'm going to do synthetic division now using this to verify again that I get 0 as my remainder. Multiply -2, 6, and 0. Okay, so doing that part quickly, but you should be pretty good at that by now. So here's what I know. So since g of x, since -3 is a 0, the factor would have been x plus 3. And what do I have left? I've got this little sad depressed polynomial here. This would be my squared, my linear term, and my constant. So I would have x squared minus 2 remaining. So I can apply the ZPP, and I know that my 1 is x plus 3 equals 0, giving me the -3, which I already know. And this one, x squared minus 2 equals 0. Well, how do I solve this? I can add 2 to both sides. Then I take the square root of both sides, and the moment I do, I need to remember that I need plus or minus. There's 2 solutions. So my actual zeros would be -3, the square root of 2, and the negative square root of 2. So there are 3. One of them is rational, and notice that these 2 here are irrational. Okay, we will physically see it cross the axis, but it happens at an irrational value. Okay, again, we're finding all of our zeros. So you're given small numbers here. Factors of p would be 1 and 2. Factors of q would just be 1, so plus or minus 1. So my possible rational zeros would be in the list of p divided by q. So I only have 4 values to check this time: positive and negative, 1 and 2. So again, pause the video, substitute in, and see if you get a remainder of 0 for any of them. I get negative 2. So if I plug in negative 2 using synthetic division, I should get a remainder of 0. So bring down the 1. Now multiply and add. Multiply again. I just realized I dropped a negative right there. And add would be positive 1. Multiply. And there's my remainder of 0. So that means that currently my function would be h of x is equal to x plus 2, that would be the factor, times x squared minus 3x plus 1. Now, if you've factored enough, you're going to look at this and go, there's nothing that I can factors of 1 there that are going to add to negative 3. So how am I going to find the zeros right there? Well, this first one is, of course, x equals negative 2. But here we can go to the quadratic formula. So x is equal to negative b would be 3 plus or minus the square root of b squared, which is negative 3 squared, minus 4 times a, which is 1, times c, which is 1, all over 2 times a, which is 1. So I'll quickly compute my radicand. That would be 9 minus 4, which is 5. So I get 3 plus or minus root 5 over 2. So my other two solutions are right here. These could be expressed also as 3/2 plus or minus root 5 over 2. So here are my 3 actual zeros.